Hello, everyone, and welcome to this lecture for ATMO 620 for fall 2020. Today, we will start to talk about the physics that we care about for this class. Last time, we talked a little bit about the math that we will be using, and today we will officially start to look at the physics. In particular, today we will introduce a topic which probably most of you are familiar with, which is that of ideal gases, okay? We will see what an ideal gas is and some of the basic properties that are relevant for this class. As we said many times, this class is about what would happen to a parcel, essentially, that doesn't move, if you will. Okay, so neglecting the dynamics and the dynamical processes that can happen to a parcel, what else can happen? The first thing that can happen and that we need to be concerned with is internal changes to its energy, entropy, heat, temperature, water vapor content, and so forth. In order to understand that, we must understand what a parcel of air is, and more fundamentally, what a gas is. Okay, and so today we'll start talking about gases, and we will do so with essentially in the simplest possible way by talking about an idealization of a gas that in physics is known as ideal gas. Now, the story of ideal gases, or the science that goes behind ideal gases, is very old. People started to be concerned with gases and properties of gases pretty much at the dawn of physics. Not really at the very start. I think dynamics and mechanics were most sort of the topics of greatest interest when physics started in the Middle Ages or at the end of the Middle Ages. But gases already in the 17th century were already raising the interest of many scientists in Europe, particularly in France and in Britain, and we'll see some of the results today when we talk about the ideal gas. Now, what do we mean by a gas? First of all, so we know and we have common experience with three types of state of matter. There is solid, in which the molecules of the material are pretty much locked in place, and they don't have a lot of possibilities to move around. Then there are liquids where molecules of the substance that you're dealing with are kind of influencing each other. They are attracting each other a little bit, but more loosely than they do so than in a gas. And than in a solid. And finally, a gas in which molecules do kind of feel each other attraction, but very, 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 very weakly compared to the other states of matter. There's also plasma as a fourth state of matter, but we will not talk about that. So, in our common experience, a gas is sort of the most, it's a state of matter where molecules are at their freest, if that's even a word. Now, in the solid, because the molecules are so tightly packed and cannot move, there isn't a whole lot that can happen. Well, actually, there is a whole lot that can happen. But, as far as molecules are concerned, they kind of stay in place and that's that. But in a gas, on the other hand, because molecules can move around, you should expect that, first of all, there are a lot of collisions between these different molecules, okay? Different gases are made of different molecules, and their collisions look kind of different, and they have different properties at different energies. But essentially, when we will talk about gas for this lecture, for the next few lectures, we will talk about an ideal gas in which molecules are essentially represented by hard spheres. So instead of having a complicated molecule, let me draw on the slide, a complicated molecule that has different polarities and that has a magnetic field, an electric field, and this is the electric field that I'm drawing. that you need to take care, you need to take into account. Now we will just think about a molecule of a gas as a single, as a billiard ball, if I got the word right. And this is what we mean by the ideal gas. Notice that one of the most fundamental properties of gases is that they exert a pressure. Okay, so liquids and gases are, because they can move around, they're typically contained in something. Okay, and the molecules of the gas exert a pressure on the container in which they are. What is the pressure? Well, we will see this for the rest of the class, but essentially, if you imagine that you have your container, okay, and you have, let's close this container, and you have all these different molecules, and these molecules are moving around at, any angle, at crazy speeds. The pressure is essentially the sum of the force that these molecules exert on each side of this container, okay? And these molecules will bounce from the walls of the container. And if you take the total force that is exerted by all the molecules that are bouncing from the container, you divide it by the area, by the surface of the container, you obtain a quantity that is known as pressure. Pressure is essentially force per unit area, and we will use pressure a lot for the rest of this class. Okay, so let's start with the ideal gas. And I don't want to start, I'm sure you're probably familiar with this equation, PV equals nRT. But before we get to that equation, I just want to start with a little bit of history and derive this equation so that we can appreciate how we got there to that formula. So our story today begins in France at the end of the 18th century, and begins with a guy called José Louis Gay-Lussac. So the surname is Gay-Lussac. Voila. Who lived from? That's not important, but just to give you a context of the age, that sort of the era that we're thinking about. So this is end of 18th century, beginning of the 19th century. And so this person was doing a lot of experiments at home in his lab. If I'm not mistaken, actually, he died because of an accident in his lab. I think he blew up with his lab. So, let this be a reminder that you should always be very careful when you tinker with things at home. If you're trying to do, don't try this at home. Okay. Anyway, so he was playing with gases at home, and he discovered a particular kind of relationship. So he discovered that when you keep the pressure that we just defined of the gas as a constant, okay, and you play with the volume of the gas, well, the increase of volume of a gas is proportional to the increase of temperature of the gas, and also proportional to the volume itself. So if we were to write this down in formula, we would have that the increase of, let's say that the gas has some temperature T0 and some volume V0, and pressure is P. Then an increase in volume, dV, is related to, first of all, the volume, and it's related to the increase in temperature of the gas. And this relationship, we will represent it, we could represent it with a simple constant. So we can multiply this by a proportionality constant alpha, which is a constant, so it doesn't change, and an equal sign, okay? dV equals alpha V0 dt. This is known as the first law of Gay-Lussac. So, first law of Gay-Lussac. this will be included in the ideal gas law, but it's good to know it. It's good to keep it in mind. The proportionality constant alpha, you can actually measure it, and equals 1 over 273 Kelvin degrees, which is, it's 0 Celsius degrees or 32 Fahrenheit. Although, be careful, whenever you do calculations, you should always use Kelvin. Do not use these fake temperatures, okay? Because otherwise you could do, otherwise a division by 273 would look like a division by 0, which doesn't make any sense mathematically. So remember, always divide by Kelvin degrees. Do not, under any circumstances, divide by Celsius degrees, and please don't use Fahrenheit. Okay, so far this is this law here is a differential law, meaning that it's kind of a differential equation, if you will, right? So we can actually integrate this. We can integrate Gay-Lussac law. Let's say that your system goes from volume V0 to volume, let's just call it V for simplicity. Okay, so you can integrate both terms. This goes from volume V0 to volume V in dV. Okay, and this one, because in this case the variable is T, we're not integrated over volume, we'll integrate it over the changes in temperature. So this goes from T0 to T. Let me simplify life here. Let's say that T0 is 0, okay, so that everything becomes simpler. And this is alpha V0 dt. You solve the integral, and you obtain, you can do a little bit of math, and you obtain that V minus V0 equals alpha V0 times T. Otherwise, it would have been T minus T0, but I mean, you see that it's not a big deal. And we can rewrite this as V equals to V0 that multiplies alpha times T plus 1. I think we can all agree with this, right? Okay, so why is this interesting, and why is this adding anything to what this equation? Well, it's not adding really much, but it's just making us understand one thing, that in this law, V and T are linearly proportional, okay? And this is first thing to keep in mind. And so even if you don't know what alpha and V0 looks like at constant pressure, this tells you that two states of a gas that are related, that have a volume V1 and temperature T1 and volume V2 and T2 at the same pressure, you'd have to have that V1 over V1 over T1 equals V2 over T2. So good old Gay-Lussac discovered this by experiments. Excellent. Okay, so much for the first law of Gay-Lussac. Gay-Lussac, however, continued to play at home with his gases, and found another law that we shall call the second law of Gay-Lussac. I hope you can understand my writing, by the way. Students have complained in the past, so please let me know if you cannot understand, you cannot decipher what I write. Anyway, so the second law of Gay-Lussac essentially tells us that by holding the volume of the gas constant now, so before it was pressure, now let's keep the volume constant, okay? So you put it in a container and you don't change the container. Then an increase in pressure is proportional to an increase in temperature and of the value of the pressure of the gas at temperature equal 0 Celsius degrees or to 173.15 Kelvin degrees. So in differential form, what does this look like? Well, we said a change in pressure is related to, first of all, change in temperature, then the value of the pressure of the gas, then some other proportionality constant B equal. Okay? In general, whenever you have a relationship, something like dP proportional, this is the proportionality symbol that I drew horrendously. Just don't want to make it look like an alpha, but proportional to P0 and dt, you can always make this equal to something times a constant. Okay. Well, not always, but in most cases, you can get away with it. Well, now you can repeat all the procedure that we did for the first law of Gay-Lussac, and you find, surprise, surprise, that P equals to P0 times some proportionality constant beta times T, temperature, plus 1. Temperature is in Kelvin. Okay, let's not make mistakes here. And so, once again, this is also the same as saying, look at this and this. Pressure and temperature are linearly related. And so if you have two gases at constant volume or two states of the same gas, pressure P1, temperature T1, and volume V. Pressure P2, temperature T2 at volume V. Well, then P1 over T1 equals P2 over T2. Okay, very good. So these are the first two laws of Gay-Lussac, which are pretty interesting and very important. There was another law that actually preceded Gay-Lussac's law, and this was a law that was discovered by an English person named Boyle. Boyle, not as in boiled potato, but as in Boyle. This person actually lived in the 17th century, which is quite surprising. That I don't know. It's always surprising when there are interesting discoveries so far back in the past. Not that I think that people back then were stupid, but it's kind of remarkable that they achieved already so much. And Boyle, for those of you who remember physics, Boyle was Hooke's teacher. Hooke's teacher. If you don't remember who Hooke was, well, Hooke was the person who discovered the law that applies to springs, that the force that is exerted on a spring is proportional to some constant K times the displacement of the spring, something like that. Anyway, just so that you know, this was Boyle. Anyway, okay, so Boyle discovered that there was, much like there was a law that regulated, as later would discover Gay-Lussac, that regulated pressure and temperature, volume and temperature, the pressure and the volume were also related of a gas if you held temperature constant. And so Boyle discovered that if you hold temperature constant, then this relationship holds, that pressure times volume is a constant. Or if you want to write it, similar to how we wrote this, you'd have that P1 V1 equals to P2 V2. Okay? Which is interesting. That's another law. And finally, going back to the 18th century, an Italian person named Amedeo Avogadro, I expect everyone to pronounce his name with correct, perfect, immaculate pronunciation. Amedeo, I'm just kidding. Avogadro, discovered something interesting about the volume of the gas and the number of molecules contained in the gas. Now, Avogadro lived, if I remember the dates correctly, 1776 until 1856. Okay, and well, we take it for granted now that gases are made of molecules, but back then it wasn't for granted at all. And in fact, nobody ever believed, well, it's a bit of a strong statement, but people were extremely skeptical of Avogadro's result because a lot of people did not believe in molecules at the time. People believed in continuum matter or something like that, but they didn't believe that matter was discrete and made of tiny things, called molecules. But anyway, he has this interesting result that the result goes back to 1811, that essentially the volume of a gas, volume occupied by a gas, is proportional to the number of molecules by some proportionality constant. Call it gamma. Call it gamma, call it A, I don't know, A for Avogadro, times number of molecules. And an interesting, so Avogadro, you may remember Avogadro because he discovered another number that, he discovered a quantity called a mole that is a type of, sort of an amount of substance, essentially. And he discovered that a substance of a particular weight in grams and with a weight that equals the molecular weight of that particular substance always contains the same amount of molecules. So I hope I'm not saying silly things, but 1 gram of hydrogen equals a mole of hydrogen and contains a certain amount of hydrogen molecules. If you take 16 grams of oxygen, 16 grams of oxygen contain exactly the same number of molecules as 1 gram of hydrogen. And the number of molecules, Na, is known as the Avogadro number, which you should all remember. It's 0.23 times 10 to the 23. This is what defines a mole. Anyway, this was a little historical detour. But what matters to us right now, it's this law here, and this law here, this law here, and also this law here, otherwise known as Gay-Lussac's first law. Okay, so we have all these 4 laws, and well, there are these 4 laws, and they all kind of talk about the same thing. They all talk about gases. In one case, you have to keep pressure constant. In the other case, volume constant. In the other case, well, yada, yada, yada. But chances are that we can probably condense all these different laws into one single law. Okay. We can show how to do so mathematically in a very simple way. Consider an ideal gas with a state PV and T, okay? And now keep the volume constant and move this gas to a different state, which we will denote with P1. Volume we said is constant, and temperature will indicate it as temperature T prime, okay? Now, volume is constant means that we can use Gay-Lussac's second law. And by this law, P1 over T prime equals P over T. Or P1 equals P times T prime over T. Now, keep temperature constant and increase the volume. And let's go down to P1. The new volume will be V prime. Temperature remains constant, so this remains T prime. Okay, let's use Boyle law. And Boyle law says that, keeping this constant, so these two Sorry, my bad. Let's cancel this one. I was a bit confused myself. Temperature is constant, but pressure is not. And so this will go to P prime V prime. Okay. So Boyle's law says, well, P1 V equals P prime V prime. Right? Makes sense. Okay. Now, if we put everything together, now we have that, we can write it here. PV over T equals P prime, V prime, T prime. And this is some constant that we will call A. Okay? And so we're already starting to get somewhere with this. PV equals A times T. Now, however, if we use Avogadro's law, okay, well, with Avogadro's law, essentially, we can find that A is the product of some constant that we can call a gas constant. And Avogadro defined his law in terms of volume, but this is also true in terms of the mass of the gas. Or if you will, we can talk about the number of moles, if you prefer, times some other constant K. And with all these together, pressure times volume equal the number of moles times some constant times temperature, or the mass times R times temperature. And this is what we call the ideal gas law. Sorry, let me rewrite law. There you go. Okay, the ideal gas law. So the ideal gas law is pretty old, and it's a very important result because essentially it relates the three most important variables for an ideal gas. Okay, pressure, volume, and temperature. Okay, and obviously the mass of the gas or the number of moles of the gas. Okay, the quantity of the gas. And it relates all of these together in a simple way. Notice that everything is appearing with a linear power, okay? The power of 1. It's not PV squared or PV to the 3/2 equal to something to the 5th power T to the imaginary unit or whatever. Let's delete this horrible thing. It's just a very simple law. Everything is linear and simple and easy to use. Okay, so this is how we represent it. PV equals nRT. There are obviously many different ways to many different conventions. Some people write the constant. Well, the constant here, I wrote it as K. The book that I suggested you follow writes it as R, and this is called the universal gas constant. It's obviously the same thing, but just know what we're talking about. You know, just know what constant to use. And this is very, very important that you always know what constant you're using. Okay. For the ideal gas, the universal constant equals this one. Rg is 8.314 joules per mole per Kelvin. And this does not depend on the gas that we're using. Okay, if you're using nitrogen and you want to approximate nitrogen with an ideal gas, the gas constant that you use, it's still going to be this one. There are other ways to write this where instead of the number of moles, you'd use the molecular weight of the gas. And in that case, because you're making it a bit more gas specific, because now you're not using the mole, which is kind of a more ideal quantity to use, but you're using something that is more gas specific, like the molecular mass of that gas. Well, the gas constant is also going to be gas specific. So, just keep that in mind. Also, know that this is an interesting fact. the ideal gas, the universal gas constant, is actually a combination of two fundamental constants. The first one is the Avogadro number that we saw before, 6.023 times 10 to the 23, and the Boltzmann constant, which we will see later on today and countless many times in this class. So this is pretty interesting. Okay, so this is first interesting result. With the ideal gas. Okay, so as I was saying, sometimes you can make the universal gas constant gas specific, and this could be advantageous because if you have PV equals number of moles universal gas constant times temperature, but you can also write this as molecular mass times another constant R times T. Now, mass over volume is is density. Sorry, I got carried away. And so this you can write as P equals to rho R T, where R is now the gas constant that is gas specific, okay? And rho is simply the density of the gas that you're talking about, okay? For air, we will see this quite extensively throughout the class. For air, the gas constant for air is 287 joules per Kelvin per kilogram, and this is a number which you will remember forever if you keep doing this job. Okay, some quantities that are important when talking about gases and ideal gases. The first interesting quantity is the so-called mean free path. Okay, what is the mean free path? We said that gases are made of many, many, many molecules, and these molecules are going around, they're bouncing off of each other, they keep colliding, etc. Well, what is the average distance that a molecule can travel before it hits another molecule or it gets hit by another molecule? Well, this is essentially what the mean free path measures, okay? And the way to determine this, the way that one can compute this is instead of having many different molecules, one could assume that is dealing with a large molecule with a certain radius R0, compute the volume that this molecule travels in a certain time, okay, delta T, and then count how many molecules are contained in that element of volume. Now, I don't want to waste too much time doing the whole derivation, but essentially, if you do the calculation, you'd find that the mean free path that is often denoted with a lambda is 1 over the density of the gas times this quantity here, sigma c, and this is called the cross section of the molecule, okay? This is essentially the density, the number of moles within a certain volume, if you will. What is a cross section? I don't know if you're familiar with this term, but essentially the cross section is how large does a molecule appear to the other molecules? Okay, suppose you have two objects that are colliding off of each other, two spheres. Okay, suppose you have a sphere that is of radius r and another sphere that is of radius big R. Okay, we'll encounter this situation many times. Now, this is a sphere, and I wish I knew how to draw this three-dimensionally, but this is supposed to be a three-dimensional object. But when you collide against it, it's always going to look like a circle, right? So instead of a sphere, let me write down a cylinder. Okay, this one I know how to make it look a bit three-dimensional. Suppose you have the cylinder. Okay, and the cylinder is, it has a certain volume and a certain surface, radius r, the height is h. This is a three-dimensional object, right? That lives in 3D. But when you collide against it, when you travel in this y direction and you collide against it, what you see is not the cylinder, but what you see is what you have in front, which is this object of height h and length 2r, right? And so even though this is a three-dimensional object, what you'll collide against is a 2D object, if you will, right? And so the cross-section is the area where you could collide with this object. And in this case, in the case of the cylinder, the cross-section of the cylinder is going to be 2r times h. In the case of a sphere, the volume of a sphere is 4 over 3 times pi times r to the cube. But when you collide against a sphere, what you're seeing while you're colliding is a circle, okay? And the circle with a radius r has an area pi r squared, right? And this is the cross-section of the sphere, okay? So when we talk about cross-section, this is what we mean. Here I wrote a square root of 2 because actually it turns out that if you do, this is a very simple calculation. If you do the calculation correctly, taking into account secondary effects and whatnot, then this formula would require a square root of 2 in front. Okay, so there's another few interesting results that we can derive. That we can derive about gases, and they involve what is known as the kinetic theory of gases. This is a bit more sophisticated than the simple, Gay-Lussac law and Boyle law, et cetera, et cetera. And this really requires that we think about the molecular structure of the gases. And it's important. Kinetic theory is important because it gives us a way to understand macroscopic properties like pressure and temperature in terms of microscopic properties like the velocity of the molecules in the gas, their masses, their momentum, their energy, and whatnot. And so it's important to keep both perspectives in mind. We'll now see a couple of interesting results that one can obtain from kinetic theory that are relevant for us. First of all, let's start easy with a cube of side L. Okay, so what I'm showing here is the cube seen from above, but if I can use my horrible drawing skills again, you should really think of a box like this, right? With side L. Perfect cube. Inside of this cube, you put this molecule, okay? The molecule is going towards one of the walls. In the interest of simplicity, let's say that it's going to hit the walls at a 90-degree angles, okay? Because otherwise there will be reflections to take into account. And let's say that the molecule has mass m0, it's proceeding at velocity v0, and it's going to go against the wall. Now, the molecule is actually a rigid ball. The side is perfectly rigid, and so what happens? Well, if you ever played squash, you'll know exactly what happens. The molecules hit the walls and gets reflected back. Now, if you remember physics, how does it get reflected back? Well, if it had mass m0, velocity v0, everything is perfectly rigid, well, it'll be reflected back again with mass m0 and velocity minus v0, because now it's going the other way. And so momentum going in, P in was m0 v0. P out is minus m0 v0. Well, v0, m0 times minus v0, but you see what I'm coming from. Change in momentum, p in minus p out is 2 m0 v0. Okay, simple. What is now this will keep going. It will maintain its velocity, no accelerations, no decelerations. We know the velocity, we know the length of this side. What is the time between two reflections? Well, the time between two reflections is the distance divided by the velocity. So the time is the distance traveled, 2L, divided by the velocity. Why 2L and not L? Because this is two reflections. Okay, so it's L, so it's L, sorry. It's L plus L. Okay, excellent. Now, every time the particle is reflected on the wall, then the particle exerts a force that is an impulsive force on the wall. Okay. The rate of the impulses is the change in momentum divided by the time, right? The impulse is proportional to the change in momentum. The rate of impulses is proportional to the change in momentum divided by the time, quite simply. And so change in momentum, we can do it, we can do it somewhere here. Change in momentum, we said it's 2m0 v0 divided by this guy here. So divided by 2l over v0. And so this is v0 over 2l. To simplify, the v0s become a power, and this becomes m0 v0 squared divided by L. Okay, so let's assume now that instead of having one molecule, we have many molecules. How many? Well, let's say that we have a density of molecules n0, certain number of molecules per volume, and let's say that the volume is L cubed. This is the total number of molecules. And let's say that 1/3 is bouncing in one direction, x direction, 1/3 is bouncing in the other direction, and 1/3 is bouncing in the other direction. So the molecules that we will be interested in for one of the bounces is this number divided by 3. And so the total force that is exerted on the gas, on the box, in one dimension is the rate of impulses, so the impulsive force exerted by a molecule, times the number of molecules that is exerting a force in that direction. Okay, for simplicity, we had said 1/3, 1/3, 1/3, and so we get a factor of 1/3 for those who bounce in this direction. Okay, so the total force in this direction is exactly this. Okay, this we can actually compute this, and one of the L's simplified. This is 1/3 n0 m0 v0 squared over L squared. Okay, excellent. We can continue. Now, let's not forget that force is pressure times the area over which this force is exerted, or vice versa, the pressure is force over the area. And so go back to this guy here, okay? Excuse me, I made a mistake. I made a terrible mistake because L2 was supposed to be here. Excuse me. So L squared was a denominator. So now divide this by the area over which this force is exerted. The area, because of construction, the area is simply L squared, okay? Because remember, this is in 3 dimensions. So this is a squared, this side here is a squared of area L squared. So get rid of the L squared, take an average of all the velocities, and this is the pressure that is exerted on this wall, okay? In this direction, because we're considering two reflections of the particles. And so we're considering both reflections on this side and on this side. Excellent. And so we have our first result, that the pressure equals to 1/3 the density of the molecules times the masses of each molecule times, this is the average of the squared velocity of the molecules. A little caveat here, I'll write it here. The average of the squared velocity is not equal to the square of the average velocity. Do not make this mistake, okay? If you have, I'll give you a simple example to illustrate this. Suppose you have a system, okay, a box, and in the box you have n molecules with velocity v, n molecules with velocity minus v, okay? What is the average velocity in this box? Well, the average velocity is n times v plus n times minus v, okay, divided by 2n. And so this is 0. But if you take the squared velocity, then you have nv squared plus nv n minus v. But now be careful, this is squared divided by the total number of molecules, 2n. So the average squared velocity is v squared, okay? So be careful. Average velocity squared is not the square, the average square velocity is not the square of the average velocity in general, okay? Anyway, caveats aside, why is this result interesting? Well, it's interesting because it's connecting a quantity that is microscopic, like the velocity, the average square velocity of the molecules, with a quantity that is macroscopic, which is the pressure on a particular side of this box. The pressure you can measure, right? You can buy some kind of instrument. You can, devise some kind of instrument, and you can measure the pressure yourself. But the velocity of each molecule, or the average velocity, the average square velocity, what have you, you can't. And so this is why kinetic theory is so interesting, because it connects two worlds in a way. Something similar can be done with temperature. And if you substitute this stuff in the ideal gas law, then you'd find this very interesting result, that 1/2 m0 average square velocity equals 3/2 Boltzmann constant times temperature. Now, this is very interesting because, well, first of all, welcome to a combination that you'll see many times in your life. The Boltzmann constant times temperature, they get along really well. And oftentimes when you're thinking about energies and there's a temperature involved, chances are that there's a Boltzmann constant in the vicinity, okay? So, be used to seeing KT, because that always happens. And this is essentially, now look at this term, 1/2 m0 v squared. If you recall anything from your physics class, it should be that this is exactly what kinetic energy looks like, isn't it? And so if you assume that your molecules are hard spheres, this would be, and you have an ensemble of hard spheres, this would be the average kinetic energy of your ensemble. Well, the average kinetic energy, what does it look like? Well, it looks like the temperature of your system. So now again, here's something where, instead of the power, here's something that illustrates the power of kinetic theory, where now you're connecting the kinetic energy of these molecules, which again, you don't even know that they exist, like you can't see them, you connect it with temperature. And so if someone ever asked you, hey, what's temperature? Well, temperature is the average kinetic energy of an ensemble of gas molecules. Okay, so this is already pretty interesting. And notice also that this gives you a recipe to compute the velocity, okay? To have an estimate of the velocities, because you can manipulate this. You can get rid of the 2 here, divide everything by m0, and you have that v0 squared average equals to 3 Boltzmann constant temperature over m0, okay? Now, this is the average and the squared. You can exchange them. So as we said above, you can't, turn this around and you can't switch these two, take a square root and have the average velocity, okay? But what you can do is still take the square root of this stuff and obtain a quantity that is called a root mean squared velocity. Root mean square. Did I get the spelling right? Yeah, okay. Or RMS. Okay. This is not quite the average velocity, the average speed of the molecules, but it gives you an order of magnitude of what this actually might look like. By the way, I'll leave it to you to show that this is square root of 3 ideal gas times the temperature of a gas. Okay. Okay. Excellent. So moving on, another interesting and important result is, well, what do these velocities look like? Okay. Well, I hope you can recall some of the statistics that you've taken in your life, but Gaussian velocities are important. Gaussian distributions are important. And whenever you have a chaotic system like that of these gas molecules in a box, then it's a pretty safe assumption that their velocities will be distributed as a Gaussian. Actually, you could do simple numerical simulations and show that even if you started with whatever crazy distribution of velocities and just let these molecules in a box bounce against each other and do crazy stuff, after only a few collisions already, the distribution of their velocities look like a Gaussian. And in particular, the distribution, this is a probability distribution of velocities in a particular direction, so around the x-axis, okay, around the x-axis, is proportional to the exponential of minus the squared of the velocities over twice the square of the standard deviations, or the variance of the velocities in the x direction. The proportionality constant is not really a constant because this guy can change, but the proportionality factor is 1 over square root of 2 pi, which is interesting. It's always interesting when pi pops out just randomly. Did you think like pi is something that belongs to circles, right? And so it's always interesting. It always tells you that there's something interesting, something deeper going on mathematically than you can appreciate. It's always interesting when pi just pops out of nowhere. We're looking at a Gaussian distribution, something that looks like this. Goes up and goes down like the bell curve. This bell curve or Gaussian distribution. It's just that, but somehow there's a pi that pops out. So I will not go into detail as to why there is a pi here, but I'll always invite you to think about it whenever you see a pi. Like, interesting. Why is there a pi when there's no circles? Anyway. And why is this probability distribution useful? Well, because now, if you want to know what is the probability that if you take a molecule, this molecule has some velocity that is contained in an interval, okay, between V1 and V2, okay? You ask, hey, what's the probability that if I just take a ball randomly, like, just fish one randomly in a box, that its velocity is between V1 and V2? Well, the area underneath this curve, okay, so the integral between V1 and V2 of this P Vx in dVx, this is the probability that your particle will have that kind of velocity, okay? And there are some properties, obviously. I don't know if you can recall this. If you know what I'm talking about, great. Otherwise, don't stress too much over this. But just know the final result. Don't worry if it's not obvious why this is true. The average of the mean of the distribution is almost by definition computed in this way: V times P times dV dx. This one, you shouldn't worry how to do this integral because V, we're integrated in V, right? So this is the variable. This is an odd function, okay? This is an even function. This is P and this is V. This is the bell curve, I remind everybody. Odd means that, let me write it here in case you forgot. An even function is a function that equals to, basically if you take the opposite with respect to the origin, the function has the same value. An odd function is a function that is the same but with a minus sign in front, okay? The product, the integral from minus infinity to plus infinity of the product of an odd function times an even function is an odd function, and the integral is 0. Okay? And so even without knowing how to do that, how to do this complicated integral that involves integrating this complicated function, the integral is 0, and so the mean velocity is 0. Excellent. Now the variance is computed in this way, again by definition. And if you actually do, if you look at how this is written down, the variance is Vx minus V bar squared times P integrated over dV. Now V bar, which is computed here, this is 0. Okay, you can cross it out for this fortuitous case is 0. And so this is the integral of Vx squared P Vx dVx. But this also, by definition, is the average of V squared. Okay, so the mean squared velocity equals the variance of the distribution. Okay. Why is this important? Well, because the variance of the distribution, I mean, who knows what a variance is? But we know what the mean squared velocity is, right? Because we know that from this result, the mean squared velocity is related to the temperature of the gas. And so now we can go back to this slide where we had the variance, which we had no idea what the variance looked like. Well, the variance, it turns out, sigma x squared is this guy here, squared mean, and this is 3 kbt over m0. These guys we know how to compute, okay? This here, a priori, who knew what that could have been? But thanks to the kinetic theory, now we know what this guy looks like. Excellent. And so finally, we can rewrite the probability distribution as this guy here, again, we have our little pi, and this term here, m0 vx squared over 2kt. Fantastic. Now, this, however, is true for the x-axis. What about the y-axis? Well, we can assume that the gas is homogeneous and isentropic. Sorry, I meant isotropic, meaning that whatever happens in the x direction also happens in the y direction and the z direction completely independently and in exactly the same way. And so the probability, the distribution of all the velocities, okay, the distribution of Vx, Vy, Vz is, because these three velocities are independent of each other, is simply the product of Pvx, Pvy, and Pvz. And these two guys here look a whole lot like this guy here, changing Vx for Vy or Vz. And this is the result that we arrive to. Okay, well, excellent. We're almost done. And there's only one thing, though, that kind of leaves me a little bit unsatisfied. Well, okay, we know what Vx is. We know what Vy is. We know what Vz is. But in reality, X, Y, and Z are kind of relative concepts, okay? And it's better, maybe, since we have a homogeneous system, an isotropic system, it's better if we don't care too much about X, Y, and Z. And so it's better if we move to spherical coordinates. And it's better if, instead of talking about X, Vx, Vy, Vz, we just talk about, instead of talking about horizontal, vertical, longitudinal component, what have you, meridional components of velocity, we just talk about the speed, which is the magnitude of the velocity. Speed is defined like this: Vx squared plus Vy squared plus Vz squared. The calculation is a little bit convoluted, and we will not get into it too much. But if you move from Vx, Vy, Vz, if you move to V, okay, the speed here, well, then the probability distribution function becomes like this, okay? 4 pi V squared times this factor that comes straight from here, and this, which is pretty much invariant, unchanged. These three we changed with this rule for V squared. So really, the only thing that we obtained was a 4 pi V squared. Notice again, 4 pi V squared, which coincidentally is the surface of a sphere, right? 4 pi r squared. Interesting. Anyway, this function here has a name. Actually has two names, and everything with everything with a name, I would say, every equation with a name, you should try and remember. Well, this function is known as the Maxwell-Boltzmann distribution. And this is important because it rules over all the gases, basically. Notice the interesting thing. Now, here, when we looked at PVX, we said, hey, if you compute the mean of this guy here, the mean is 0. We saw it here. Sorry if I keep bouncing around between slides. So the mean was 0. So Vx mean 0. Vy mean is 0. Vz mean is 0. Okay? However, notice that now, when we moved from the components of the velocity to the speed, we obtained for free this V squared. And what this V squared does is mess up with the calculation. When you now compute the average speed, and the average speed will be V times the Maxwell-Boltzmann in dV. This is the speed, not the velocity anymore. Again, the speed is the magnitude, okay? So it's this guy here. Whereas the velocity is always referred to a particular direction, the x direction, the y direction, what have you. V is the speed, and it's the magnitude. There's no there's no such thing as negative magnitude, right? So this goes from 0 to infinity. Now, the mean speed now is not 0 in principle anymore, okay? Interesting result. And this is, mathematically, it's basically because of two things. First, because you got a v squared here that is going to mess up everything. And also because the integral now goes from 0 to infinity. Physically, it makes sense now because, again, you're now looking at magnitudes. You're not looking at velocities anymore. So even if half of your molecules are going in the x are going towards positive x's, the other one is going towards negative x's, their speed doesn't know anything about signs. And so when you take the average speed, it makes sense that it's not 0 in principle. Okay. So as a last couple of things, now, if you compute the mean speed, and don't do it because it's a bit complicated and you probably have better things to do. If you compute the mean speed now, this is, not only is it not 0, but it's this thing. Square root of 8 Boltzmann temperature over pi over m0. Once again, that pi is flying around. Now, remember what we said before, that the root mean squared velocity had a 3 kt m0. And also, the standard deviation of the distribution is kt over m0. So you may be wondering, well, I mean, what are we supposed to use? Like, which is which? What is the most useful thing to use? Well, the real answer is that I don't know. It really depends on what you're trying to do. You know, what is it that you're trying to compute? Are they that different, these things here? Well, this one has a 3. This one has an 8 over pi. Okay, pi is what? 3.14, more or less. So 8 over 3.14 is something slightly lower, slightly less than pi. Slightly less than 3. And so it's not particularly different. And so if we think about air, then the root mean squared velocity of air, you can compute it. For air, this is something like 508 meters per second, which is a lot. The mean speed is, if I computed it correctly, 467 meters per second. So, yeah, they're different, but they're not that different. Another way that you could compute the speed is the so-called mode velocity. And the mode velocity is essentially the velocity at the peak of the distribution. And the mode velocity, V mode, this can compute is actually 2k Boltzmann T over m0. And this is 415 meters per second. So just to give you an idea of how, and this one, if you compute it, this is 293 meters per second, which is also a lot. Like standard deviation 293 meters per second is pretty big. It means that 60, well, I mean, no, it's not a Gaussian, but it's pretty big and a considerable, you could have a considerable portion of your molecules with velocities that go from 200 to 700 meters per second. Okay, just to give you an idea. I was saying that 66% are between a standard deviation, but Maxwell-Boltzmann is not a Gaussian, okay, because it has that v square in front, okay, and it's not defined for negative values. So I'm sorry, I was going to confuse you. Just to give you an order of magnitude of how big these things are, well, the speed of sound, which is, I don't know how many remember this from physics, but velocity of the speed of sound, not the velocity, is square root of 7 k Boltzmann t over 5, so it's lower than that, m0, and in the air, that's about 331 meters per second. So, I mean, yeah, pretty big. Okay, so this was just to give you an order of magnitude, and I would always recommend whenever you learn some formula like this, just plug in the number just to see what it actually looks like. You know, how big are they? What are the scales that we're talking about? And also, another thing, what we said for this distribution, that, if you want to know the probability of finding molecules with velocity between v1 and v2, holds true for this one as well. So now the Maxwell-Boltzmann distribution will look something like this, goes up rapidly and then decays. Let me redo it because it didn't look good. So it goes up rapidly and then it doesn't actually cross the zero. Okay, it goes down like that. If you want to know the probability that your molecules have a velocity, have a speed that goes from v1 to v2, it's the area behind this curve. Okay, excellent. Last thing that I would like to tell you in this class is the Dalton's law. I don't know if this is the right way to pronounce this surname, but we'll go with that. Essentially, the ideal gas is great, but it is a bit too ideal, and it only talks about one type of molecules. In reality, we will deal a lot with air in this class because we're interested in the atmosphere, and the air is made of many different gases, chiefly nitrogen, which makes up about 78% of the air that we breathe, oxygen, that only accounts for 20%, roughly, and then argon, water vapor, and CO2 are a little bit less. Dalton's law tells us that the pressure of a mixture of gas is the sum of the partial pressures of each individual gas. So the pressure, so if you have a parcel of air, and this is contained in this sphere of radius r, sphere S, the pressure that the gas is exerting is the sum of the pressure due to nitrogen, the pressure due to oxygen, the pressure due to argon, and so forth. Which intuitively it makes sense because you are summing together. Remember, pressure was due to changes in momentum. And so it kind of makes sense that the total change in momentum is due to the sum of the changes in momentum due to the different molecules. And so this is a very interesting formula, a very nice formula, and it's very useful because whenever we deal with clouds, for example, we're often trying to pay attention to what happens to the water vapor and what happens to the dry air. And thanks to Dalton's law, this gives us a simple recipe to connect the two, to connect dry air and to connect water vapor and to compute their properties. Okay, this concludes this class. Please let me know if you have any questions. The contacts are on the slides at the beginning of the class. Here they are again. If you have any questions, any doubts, and you want to communicate with me, anything that was not particularly clear, please shoot me an email, call me on the phone, and I'll be happy to answer to all of your questions. Thank you very much.